we're going to have a look at slope fields, the last of our topics in the area of differential equations, guys. This is an approximate technique, as was our last technique, Euler's method for solving differential equations. We've got a lot to cover, so let's have a look. What are slope fields? Well, they're very interesting little beasties, as you'll find out in a moment. They are another method of finding a graph from a known derivative function, okay, but a sketch graph, right, just a sketch graph. A two-dimensional array of x and y positions is set up on a Cartesian plane, okay, just similar to this pattern here, you know, intersecting x, y positions in a sort of a matrix, yes, on a two-dimensional Cartesian plane is set up, and then based on the known gradient function, e.g. dy dx equals 2x or something like that, what you do is you work out the gradient at each of those points in that matrix of x and y positions based on the known formula for dy dx, and then at each of those points in your matrix of x and y positions in the two-dimensional Cartesian plane, you draw or sketch a little mini gradient line, because you can work out what the gradient is at each of those points. So you draw a little sketch line denoting the value of that gradient, the slope at that point, and then they're drawn right at every single point along that two-dimensional array, and you get this little field of these little slope lines, and it looks amazing. Then what you then do is, if a single known point on the parent curve is known, if you know one single starting point on the parent function, then what you can do from these slope fields, you can actually sketch out a reasonably accurate sketch of the parent function, okay? But the way you do that, I'll show you in a moment. You can sketch it using those slope lines, always sketching parallel to the slope lines in the most immediate vicinity. Okay, now, if that all sounded crazy, don't worry, I'll show you and you'll get the idea. If we had dy dx equals 2x, alright? Now, this, ladies and gentlemen, is the slope field matrix, which denotes that situation. So, just to illustrate what I'm talking about, if x was, let's say, 1, right? Dy dx would only depend on x, and therefore it would be always 2 when x was 1. So this right up and down here, okay, no matter what the value of y, because y is not even in the dy dx formula, it's only 2 times x. So when x is 1, dy dx would be 2, right? When x was minus 1, dy dx would be minus 2. When x was 2, dy dx would be 4, and you see there's steeper lines there when x is 2 compared to when x was 1, for example. When x was 3, then dy dx would be 6, so you're getting really, really steep lines now. Similarly, when x is minus 3, dy dx would be 2 times minus 3 or minus 6. You're getting the idea now, you see? This is the slope field situation, where at every point in our little two-dimensional matrix of x and y positions on our Cartesian plane, we're working out the slope, and we're putting a little mini slope line there to denote what the slope is, right? Now, check this out, guys. If we have a known point there, say x is 0 when y is 0, we can start off at that point, and we can start tracing out from that point what the parent curve would look like, always running parallel to the nearest slope line and never ever crossing through a slope line, because that would be very bad, because you remember that you're always running parallel to the tangent line on the original curve. So you can't cut through a slope line, because if you did, you'd be running at a slope which would be very different from the nearest slope line in that vicinity. They always have to run parallel. Okay, parallel to the tangent or slope lines. So you would go like this, starting there, and you'd go, okay, and this is only a guesstimate, you don't get too hung up over it, you just do the best you can. See, I'm going to run there, I'm going to run parallel to that slope line. Up here, we'll see where we go. Okay, we're getting up there, now we'll still run parallel, 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 parallel. Yeah, that's about it. You know, that's the way I'm going to do it. Now go on the other side now. See, running parallel to the slope lines, never running through one, don't cross through one. That looks pretty good. That looks pretty good, doesn't it? Yeah? Okay, now here over what have I said there? Sketching the curve, always trace the curve with gradient guided by the nearest slope field lines and never crossing through one line or intersecting going through one, yeah? Because that would indicate you're running at a different gradient from the nearest slope line. No, this is the real thing. This is the real deal, which my calculator computed for me. See, so I wasn't too bad. I was pretty close to what the computer worked out, yeah? Fascinating, isn't it? See, we've got a sketch now of the original parent function based on one known point and all this field of slope lines. They are indeed fields, aren't they? Yes, so that's the concept. Yes, I know, it's mind-boggling, isn't it? Very interesting. Wonder who thought that up. Now we're going to do some practical examples of some exam questions, all right? Let's go with this. These are exam 2 questions, which are tech-enabled questions. You can actually set up this thing on your calculator when you're in the graph screen. If you go to not function mode, but differential equation mode on the TI CAS handheld device, which is what we use at my school, you get these crazy things. If you enter in any kind of derivative function, and you hit enter, my goodness, it's an abracadabra of an amazing kind, because you get all this stuff appearing on your calculator screen, which just causes your eyes to go like saucers and your jaw to drop to new low positions, because it's like nothing you've ever seen before on your calculator. So why don't you give that a try? I'm sure you'll be amazed. Anyway, meanwhile, back at the ranch, the differential equation that best represents this thing, well, blowed if I know. However, I always do a few things when I'm checking these things. I'll soon find out what it is. The very first thing I do is I sweep along the x-axis. I see what's happening to the slope lines as a reference point when y equals 0. Then I sweep along the y-axis when x is 0, and I have a look what's happening. And that tells me a lot. First of all, I look to see whether the gradient changes. Say for when y is 0, I see if the gradient's going to change along here. That will indicate if it's, well, we've got a situation here where it's basically vertical. So it's not changing, but it's also vertical. If it changes and it's not vertical, that indicates to you that, yes, the gradient depends on x when y is out of the picture, because y is 0, right? But these are not changing. Similarly, I sweep along the y-axis to see what the slopes are doing as y is changing and x is out of the picture, because x is 0. And it tells you a lot. It tells you a lot, guys. In this instance, I can see some very interesting information. I've got 2 special cases here. Along the x-axis, the slope lines are vertical, which means the gradient is undefined when y is 0, okay? Yes, and along here, the gradient is 0 when x is 0. So that tells us something pretty amazing. So, as I've said there in my explanation, when x is 0, which is the y-axis, dy dx equals 0, right? All along here, yeah? All along there, where x is 0. So that tells us, as we'll see in a moment, yeah, probably a single term, that's what it tells us, with x on the numerator, because if dy dx is 0 when x is 0, that's like having x in the numerator, isn't it? So I think I'm getting very suspicious that this could be right and this could be right. That wouldn't be right, because when x is 0, the gradient is 0 no matter what the value of y is, right? So that can't be right. And similarly to this one, they can't be right. They're out of the picture, they're out of the running. This is wrong. It's either this one or this one, right? So when y is 0, that is along the x-axis, we can see that the gradient is undefined, vertical line. So that tells you when y is 0, y is probably on the denominator, okay? Y is probably on the denominator because anything over 0 is undefined, okay? That's that one. Okay, now we've got to work out the final battle between D and E. We've honed in on it very quickly. Now, how are we going to work out whether it's a minus x over y or whether it's a plus x over y? Well, I think what I would do is I'd go in here and say, okay, let's just pick an example. When x and y are both positive, there you can see that the gradient is positive. So therefore, this is no good because that would give you a negative, right? This would give you a positive, so I'm saying it's going to be E. Yes, it's E. You get it? Isn't it fun? It is fun, believe you me. When you get good at them, they're really fun. Now, I don't know how well this is going to come up on the video. These are very faint. They're very faint. But look, see this here? dy dx is xy. Now, that's a pretty unusual one, and these graphs are absolutely all over the place, these slope fields. But if you think about this for a few moments and don't get all stressed and just let your head get into gear, you can very quickly work out what's going to be the right solution to this, because you can think about this as I will describe to you. When x is naught, according to this formula, dy dx would be naught. So you check out whether that's the case, right? And when y is naught, you'd also be expecting dy dx to be equal to naught. So you want flat lines along here, and you want flat lines along there. So that might just knock some of the contenders out of contention, yes? And the other thing is, this is very interesting. You can analyse what happens when x is positive and y is positive, where one of them is negative, and when both of them are negative. Because when x and y are both positive, you expect the gradient to be positive. When x, y is when one has a different sign to the other, you would expect the gradient to be negative, as I've said there. Yes, when they have the same signs, they'd be positive. That's the other thing, when they're both negative or when they're both positive. Now, the only graph that actually, in case this doesn't come through on the video properly, which I'm a bit suspicious, to fit them all on, I had to make them too small. So A is the only option there. A meets all those criteria, right? It's negative. It's flat along the x-axis. It's flat along the y-axis. And when they're both positive, the gradients are positive. When they're both negative, the gradients are positive. And when one of them's positive and one of them's negative, the gradients are negative. So A, hooray! A today wins the day. Great show. Now, what's this beastly looking thing? Heavens above. Well, I always do my sweep along the x-axis and the y-axis. I always do that. So this is very interesting. Look, when I sweep along the x-axis, the gradient is constant. So so therefore, that means when y is naught, the gradient is some negative value, some constant negative value. That's interesting. So when we'll do a y-axis sweep now, this tells me that when x is naught on the y-axis, the gradient is positive, but it's not as positive as to the degree to which this one here is negative when you're sweeping along the x-axis. So, but apart from that, it's very difficult to know what's going on here. So why don't we try and do an analysis of when x is naught and when y is naught and see what you get? Because we should be able to get a negative constant value when y is naught, and we should be able to get a lesser but positive constant value when x is naught, shouldn't we? So maybe we can analyse that for those 5 different cases, which is, I think, the way I did it. Yeah, so just to recap, when y is naught, dy dx is slightly but somewhat positive. That's when x is naught on the y-axis, right, over here. Yes, okay. And when y is naught on the x-axis, it's quite negative, more negative than the degree to which it is positive when we're going along this axis. So we should be able to get that from our correct option. So if we analyse the 5 options, look at this fancy looking table. What do we got here? Option A, B, C, D, E. Now, dy dx when x is naught, that's the y-axis, and dy dx when y is naught, that's the x-axis, right? Now, there's all our ducks in a row. Now, okay, so A, if we look at A, now look, when x is naught, okay, x is naught, that's a nothing, so it's just y over 2y, which just gets us a half, okay? And you can do the same thing analysing B, C, D, and E. I'll just do that quickly. If you like, you can pause the video and just make sure you agree with me. Now we'll do when y is naught, which is the x-axis. So, okay, let's have a look at this. When y is naught, that term goes, and you would get from option A minus 2x over x, which would be minus 2, wouldn't it? Be minus 2. There you go. Now you can do a similar analysis for B, C, D and E. Now we're going to work out which one is correct. So now let's just think here. Along the x-axis, when y is 0, we're expecting minus something. So when y is 0, we're expecting oh, that looks all right, doesn't it? Now along the y-axis, that meets our criteria. Look, we'd expect something positive, but less positive than the degree to which this one was negative when we were cruising along the x-axis, where y is 0. I think it might be A today. Oh, yes, it is. A is the winner. It's the only one that matches the profile above, so A is the one. Okay? You see? You just have to be a bit of a detective and don't be intimidated by these things. Right, this one here. A direction field for the volume of water V megalitres in a reservoir T years after 2010 is shown below. Oh, well, this looks very, very uninspiring, let me tell you. What do you do with this? Well, it looks like as V gets down to 0, it looks like dV dt goes to 0. In fact, when V is 0, dV dt would be 0, wouldn't it? Yeah, and it also looks like it does not depend on T, because T, as T increases, it's still flat all along the way there like that. And for any value of V, it looks like T is always the same. The slope is always the same irrespective of the value of T. You see how I'm gleaning information, getting my ducks in a row here? So I'm saying that when V is 0, dV dt is 0, and it doesn't, and the gradient does not depend on T. Yes? So wouldn't be listening to this guy. He's an imposter. This is an imposter because if it's K over V, when V was 0, you'd get an undefined gradient, which would be vertical. Well, that's no good. Neither is this for the same reason. So it looks like it's got to be this beastie or this beastie, yeah? So is it minus or is it plus? Let's do a little bit of further analysis. So what if I pick a value... Alright, let's pick a value of positive V. This is positive V, and look, I've got a negative gradient, yes? Because V is only positive in this whole thing. You haven't got any negative V's, because you can't have a negative volume, can you? So therefore, when you've got a value of V, the gradient here is negative, isn't it? So it looks like this beastie wins the day. I'd say C for you and me. Now, is that what I said? I can't remember what I said. So so V is 0, dV dt is 0. This suggests a single term with V in the numerator. Yes, it does. When T is 0, dV dt becomes increasingly negative. What did I say there? When T is 0, becomes increasingly negative as V increases. Oh, yeah, that's true. Very true. So, for a given value of V, dV dt is independent of T. Oh, that's what I said before. And C, that's what we said, wasn't it? C for you and me? Yippee. Yippee. Yes, it's C. You see, it works, doesn't it? It works. So our detective work triumphed again. Well, here's another one. This looks like an ellipse, don't you think? Definitely an ellipse, but it's these are the gradient lines of the ellipse. So the first thing not to be taken in by is this equation here. That's the equation of an ellipse, but this is the derivative we're talking about. So the derivative equation for an ellipse is not an ellipse. It certainly isn't. So A and E are imposters. So we chuck them out straight away. Don't want you, A or E. Don't lead us up the garden path, you guys. Now, what else can we do? When I first looked at this, I thought, good heavens, what am I supposed to do? Because the x and the y-axis scan don't really do much good for us, because the gradients are changing from negative to 0 about there to positive through here, and the same thing's happening with the y-axis. See, that's a little bit negative, that's a little bit undefined, a lot undefined, and that's a little bit positive and getting less positive. So that's kind of like a bit, doesn't really tell us much. But I'll tell you what does tell us a lot is this thing here. This looks like ground zero here, doesn't it? And you can see that when x is 6, the slope lines are all flat, yes? And when y is 3, the slope lines are always vertical. So if we can see that reflected in this derivative stuff over here, let's find a value where plug x equals 6 into something and say that that's got to come out to 0. Well, that would work, wouldn't it? That would work, wouldn't it? 6 minus 6 is 0. Does that work with the y thing? Y is plus 3. Oh, look. This is our baby. Y is 3. 3 minus 3 is 0, and dividing by 0 gets undefined. I think it's B. Let's see if that's what I said, guys. This, look, yes, it certainly does, Mr. Computer. We're asked for the equation of dy dx, not y. So don't be taken in by this stuff. That's not correct. That's the equation for an ellipse, e.g. a y. Yes, if you know what I mean. Yeah, well, what I'm trying to say is that, you know, this is the equation for ellipse. Usually that plus equals 1. You know, for example, for an ellipse, well, they're not. We're talking about the gradient. Well, that's just ridiculous. Okay, so there, A and E are wrong. In this example, x and y axes don't help much. No, certainly don't help much. However, from the centre point, yeah, I worked this out, 6 and 3. So I think this is, yes, you can see from that, that's what we were talking about, wasn't it? Therefore, when x is 6, dy dx equals 0, and when y was 3, it was undefined, so therefore it's B, and that's what we picked, wasn't it? B, for you and me. Very good. Okay, another one. Goodness, mind-boggling, isn't it? This definitely looks like a sine graph to me. Okay, it looks like a sine graph. The shape of it is indicating a sine graph to me. So, but again, these options are talking about the derivative. So if the graph is sine, okay, if the graph is sine, don't be taken in by that. The gradient would be cos. The gradient would be cos. So I'm very suspicious of this and this for a start. I don't think they're the answers at all. Okay, now let's just see what I said. Yes, it looks like a sine graph. Tracing lines from the origin reveals a period of pi. Okay, that's got a period of pi, I think. Don't you agree? And the amplitude is around about a half. Yes, here. Yeah, about a half. So, all right. So therefore, if sine was, say, a half sine 2x, which is what that thing looks like, then therefore dy dx would be that, wouldn't it? Which would be cos 2x. So I think here is the genuine article, don't you? I think that's it. So, yeah, B. B for free for you and me. Yep, B was right. Another ellipse, isn't it? Don't you think so? I think so. Now, let's analyse all this. The centre of this ellipse looks to be on the origin, doesn't it? Would you agree with that? I think so. And this, look, have a little axis scan here, look. See, when x is 0, dy dx is 0. Well, that's interesting. That would indicate to me there's an x in the numerator. Okay? When x is 0, dy dx is 0, irrespective of what y is doing. And when y is 0, dy dx is vertical. Right, that indicates to me there's a y on the denominator. So something x over y. I think, we got something there? Ooh, C and E for you and me. Now, we need to basically make up our minds whether it's a minus or a plus, and we do that by picking a positive value of x and y, say 1 each. The gradient's negative, so I would put my money on C. I would put it on C, wouldn't you? Let's see what I said. Scanning the x and the y axes, yes, when x is 0, that's the y axis. dy dx is 0, yes, that's true, and when y is 0, dy dx is undefined vertical lines, that's along the x-axis, yeah? So C or E, yes, very good. When x was 1, y was 1, yes, it was negative, it's exactly what I did just talking to you a moment ago. So C is the answer, okay? See, they're not so hard, are they, really, if you just put your detective hat on. Now this is the last one we're going to do. This is actually a manual one. This appeared in exam 1 a few years ago for specialist maths, and that's more unusual for them to do that to us. Okay, so let's just have a go at this. We've got dy dx. We've got no calculator now. This is all just our heads. Dy, not that we've been using our calculator anyway, but dy dx is 1 plus y squared over 2. We've got to do a matrix from y goes from -2 in whole number increments up to and including +2. Same thing for x. Yeah, well, that's all right. Look, dy dx is 1 plus y squared over 2, so it does not depend on x, only on y. So if you pick a value of y, going from here to here to here to here to here, the slope lines will all have the same gradient because it doesn't depend on x. Alright, so let's just do some. Yes, only depends on y. So the gradient lines, yes, that's what I just said. Now, let's do a little table of values here, and we'll work out some gradients. That's according to this formula. See if you agree with me. If I'm going too fast, just pause the video when this table's completed and work them out for yourself, okay? Alright, now let's keep going. I'm going to put the slope lines in now. I've made myself a little matrix by putting these little red dots in here. That gives me a guide as to the centre point of each of my little slope lines. Okay, let's put in. That's when y is minus 2. That indicates to me that the gradient is 2.5. Don't be too hung up over whether that's the right slope. It's just the roundabout will do for this, because you haven't got a calculator, and you don't have to do it super accurately, just so that it looks reasonable. Okay, so that's the first one, and that'll be the same for when y was plus 2. We got the same gradient, 2.5. Let's do the next one. This is when y is minus 1, so that means we're going to have a gradient of 1. Okay, that's sort of the trend is right, and of course the trend is your friend. There's the next one, when y is plus 1. Now the last thing to do is when y is 0, we get a half. Ooh. Right, well that's it. It's pretty mind-blowing, isn't it? That's the end of that part of the question, but of course there's a part B, wouldn't you know? So let's go over the screen. Alright, now, this is an analytical part now. We've got to solve this thing for y is minus 1 and x is 0. Solve the differential equation given in part A to find y in terms of x. Yeah, well, we can do that, guys. No problem. Fasten your seatbelts. Now, what are you going to do with that? Come on, you tell me. Yes, did you say you're going to flip it? Well, that's what I'd be doing, flip it. And then solve for x in terms of y, and then rearrange it to get y in terms of x. What do you think the integral, how are we going to do the integral of that thing? Yep, inverse tan's the man, that's the one. So we get 2 times inverse tan of y over 1, or just y, plus c. Now we better put our boundary conditions in. Looks like x is 0 when y is minus 1. So let's put that in, okay? So that, yes. Now what do you know? What is the angle which has a tangent of minus 1? It is minus pi on 4, so that term there would be 2 times minus pi on 4, which would be minus pi on 2. Therefore, C must be pi on 2. Okay, Mr. C, take your places. Take your place in the ensemble, Mr. C. There you are. So x is 2 times inverse tan y plus pi on 2. All right, now that's good. Now, but we've got to make y the subject. So let's do some pea and thimble tricks here and take pi on 2 over the other side and then divide by 2, and we'll get that. And now we just take the tan of both sides, and we get y is the tangent of that thing. And that's what we had to do, wasn't it? I think that deserves a box. Thank you, Mr. Box, and hello to you. Now, what else are we supposed to do with this thing? Sketch the graph of the solution curve found in part B on the slope field from part A. Oh, goodness, they don't want much, do they? Well, there's a solution we got from part... what am I doing there? Oh, okay, I'm trying to get all my facts and figures together so I know how to sketch this thing that we found in part B. That's the, when x is 0, that'll be the... x is 0, that'll be the y-intercept, won't it? Right, there's the slope thingies that we got from before. So that's our y-intercept. Yes, there, that's it, right? But we also need an x-intercept. We better get it right. Remember, this is a tech-free question, so that's going to be a bit interesting. And, you know, these beastly tan things can have asymptotes too. So that's... And the crazy part about this question was this last bit was only a 1-mark question, and there was so much work in it, this part C. So it's a bit off, to tell you the truth. However, we're having fun anyway, aren't we? So we need the x-intercept. So let's put y equals 0. And what do we get there? Okay, it looks like x is pi on 2. Now, this is the thing. Look, this is a tech-free exam. So hopefully you know that pi is 3.142, and half of that's about, therefore, a bit more than 1.6, because you've got to get these things with the proportion sort of right. So we're in about there sort of thing, in there for the x-intercept. And you have to get the proportions roughly right. Yeah, about 1.6. All right, now asymptotes. Oh, goodness me, for a 1 mark, I mean, honestly. However, ours is not to reason why, but we're to put that in. So we're saying that all of this thing behind the tan here, asymptotes, so all of that thingy there would have asymptotes at pi on 2 plus k pi. Remember, tan has a period of pi, where k is any integer, alright? So I've got to solve that thing for x. Therefore, that's right, multiplying both sides by 2, isn't it? And then add pi on 2 to both sides, I get that. Alright, so that looks like where the asymptotes are. Now we've got to work out where that means asymptotes are within our domain of -2 to +2. So having thought about that for a moment, I just worked it out. I went backwards. I said, well, if k was 0, x would be 3 pi on 2, and 3 pi on 2 is 1.5 times pi, which is, what's that? About 4.5, so it's well outside our shooting match over here. It's outside our domain, so that's no good. So going backwards, making k -1, you would get minus pi on 2, which is relevant to us, and this one's, again, way outside of our bailiwick here. So that's, what's that? That's about minus 1.6, isn't it? So it looks like there's an asymptote about here. Well, that's a bit nasty, isn't it? So we better make sure when we sketch this graph that we don't go any further than 1.6, because that's the asymptote. If we do that, we've really messed it up, haven't we? See what I'm trying to do? Get a feeling for where things are, get my bearings so I don't mess the graph up. So there is an asymptote, yes, at minus pi on 2, which is about minus 1.6. We have to allow, yeah, we do have to allow for any influence of this asymptote. Now, ladies and gentlemen, and only now, can we sketch the graph knowing enough about it to have full confidence in what we're doing, all right? Or at least I need to know all that information so I know there's no booby traps about to get me. Okay, so let's sketch it now. Sketch-a-rooney. There's my x-intercept, there's my y-intercept, and I've got to make sure I don't go past there. I've got to be sloping well and truly down by the time I get to about there, minus 1.6. So, okay, you ready? Let's go. It's showtime. There. Ooh, now that looks good, doesn't it? I haven't got any problems with that nasty asymptote. I didn't cross this slope line. Yeah, that's very nice, isn't it? Now we better go up the other way. So we'd sort of go like this. Something like that. Yes, do it in stages. Don't do too much at once. Yeah, that looks pretty good. I reckon we'd get full marks for that. Yes, but it's a nasty question for 1 mark, isn't it? Heavens above. I don't know what they were thinking when they said that. Yeah, but better put our thingies in, better put out all our known points to get our 1 mark, and that one as well. And I don't think we actually have to put the asymptote in, because we're really not very close. Or maybe we do, or maybe we don't, but I doubt it. So I'll just put the position there just in case. So that's asymptote position x is minus pi on 2. You could sketch it if it made you feel better. And I think that's it. Oh goodness, that's it. So you're a star and you'll go far. Now you know how to do slope fields. Weren't they interesting? I mean, what a technique. It's very innovative and very fascinating, and it allows you to put your detective hat on and to have a great time trying to unravel the mystery of what those gradient functions are as they give them to you in those multiple choice questions. Alright, you go and do some practice and have a fantastic day, and we'll see you next time.